general relativity, step by step. I've been set this task to simplify this this rather confusing. It's not confusing, but it's quite involved. I'm going to use the fact that the Riemann tensor has got this nice simplification, or nice symmetry relationship, minus sigma mu alpha beta. We can swap the first and the second pair of indices over if we change the sign. So I can use that here. So what does that give us? That gives us that G gamma sigma, G alpha mu, G beta nu, copying from here, minus this, R sigma mu alpha beta semicolon nu plus R nu sigma alpha beta semicolon mu. That's what I've got there. What does that equal? Well, that equals minus, let's just write them down. G gamma sigma, G alpha mu, G beta nu, R sigma mu alpha beta, all in brackets, semicolon nu. What I've done here is, although the covariant differentiation refers to this term here on its own, I've observed the fact that the covariant derivative of the metric tensor is 0, and I've brought it inside the bracket. The minus sign stood up there, plus G gamma sigma, G alpha mu, G, I'm just copying off here, mu down, times, now I need to use this here, R mu sigma alpha beta semicolon mu. There it is. And have I got my minus sign still? Yeah, the minus sign's outside altogether. And I've closed, no, that should be there. And I need to close a curly bracket to match this curly bracket. Ha! Equals minus. Now from the definition of the Ricci tensor, what we've got left is R with two coordinates, two contravariant indices, semicolon nu, and one of them's a nu, and what's the other one? One of them's a nu from this nu here, and that cancels with this one here, or sums across that nu there. What have we got left? We've got a gamma left, that's right. Plus R, and by the same line of logic, this is mu, but now the mu term is here, and the other one left is sigma there. I think that's right. And they're equal, because I can just rename the nu as a mu. And so that equals minus 2R gamma nu semicolon nu. Actually, I'm not going to use nu, I'm going to use sigma here just because I can. Sigma, sigma. I can call that symbol what I like. So what have I got? Just to summarise what we've got the Bianchi identities here, which I know to be equal to 0. And I've got the three terms A, B and C, and this one here, the A term, was equal to, well, let me write it out. It's here, which was this, which was equal to G gamma sigma R comma sigma. G, copying from here, gamma sigma R, all in brackets, semicolon, sigma, minus 2R gamma sigma semicolon sigma equals 0. So this is a restatement of the Bianchi identities. And just because I can, I'm going to divide by 2. I'm going to say that a half G gamma sigma R semicolon sigma, all in brackets, minus R gamma, sigma, semicolon, sigma equals 0. Sigma equals 0. Okay, and what was the purpose of doing all of this? The purpose of doing all this was to define that B there. Let me just write out this equation here. I'll copy it down here. R alpha beta plus B R G. So what I was trying to do was to show that R alpha beta plus a constant B times R G alpha beta semicolon B equals 0. That was my task, and I had to find B. Well, you can quite easily see that this term here, maybe I should multiply by minus 1, R, and then by renaming the indices, see, I can call them what I like. This gamma sigma is just going to be called alpha beta, semicolon beta, minus a half G alpha beta, again doing the same thing, put that in brackets, semicolon, sigma was a beta, was equal to 0. So that shows me directly that B equals 0. It must be equal to 0 because the Bianchi identities tell me it must be equal to 0. The only B that will do is B equals minus a half from the Bianchi identities. Very powerful things, the Bianchi identities. So let me just scroll back, see if I can find my, oh, here it is, here it is, here it is. I was looking for candidates. So before I had R alpha beta, I had this term, oh, here it is. I keep on writing it out again, don't I? R alpha beta plus lambda plus B. Let's just write that out again. My interface is misbehaving. My interface is misbehaving. Here we go. So my candidate for the field equations was R alpha beta plus gamma, no, that's a lambda, G alpha beta, plus B R G alpha beta equals the stress energy tensor, equals the stress energy tensor. But we know that the derivative of that, so this semicolon beta equals T alpha beta semicolon beta, which equals 0, which tells me that that can be anything I like, and B has to be minus a half from the Bianchi identities. So let me rewrite what we've got. We've got R minus a half R G alpha beta plus gamma, no, it's not a gamma, it's a lambda, G alpha beta equals T alpha beta, stress energy tensor T alpha beta. Why is it minus a half? It's because that was the value of B that did it, and I guess I've kind of written that there and this here. And this is a candidate for the field equations, because it works. The divergence is 0, the covariant divergence is 0. Now I'm just going to make one little change here, which is that I'm going to oh sorry, that should be alpha beta. I'm going to rewrite that R alpha beta minus a half R G alpha beta. I'm going to call that G alpha beta equals the Einstein tensor. Okay, so now I can rewrite the equation again, and this is the form that you normally see it in. G alpha beta, oh, it's a K for constant, plus gamma G alpha beta equals some constant which we still haven't determined, T alpha beta. I think I've been forgetting to put the constant in. Yeah, it's there, isn't it? I've got the constant which I've not been writing in. I guess you could get rid of that by using suitable units, but anyway. So this is a candidate for the Einstein field equations. Well, it is the Einstein field equations, but Einstein presented it as a candidate for the way the universe actually operates, and it seems to work. So what I'm going to do is to pin down this K and discuss this peculiar lambda term here. This is geometry here. This is geometry. The Einstein tensor is a feature of the curvature of space. This is a feature of space itself, I guess, and this is the mass energy tensor here on the right hand side. So I'm just going to stop there. Stop. This is the Einstein field equations. Stop.